Black holes are a common phenomenon in space we talk about like it's a normal occurrence. But what made us get here and how many theories were made in the passing time are revolutionary. But this video isn't about the history of black holes, but I will still explain some basic surroundings around black holes so we could expand on our theories. Let's start with the general theory of relativity. General relativity describes gravity as the curvature of a spacetime caused by matter and energy. Black holes naturally follow this description as an extreme consequence of this theory. Matter curves spacetimes, which means that the more massive or dense an object is, the stronger the curvature of spacetime is. The event horizon is a point through which only inward flow can pass, not outward flow. The event horizon is located right inside a black hole, and the reason nothing can escape is that the curvature of spacetime is so strong that not even light can escape. But how does a black hole actually form? First, you need a star in which nuclear fusion takes place in its core, where hydrogen is converted into helium. But when a star runs out of fuel, nuclear fusion stops. Without back pressure, gravitational collapse begins, which means the star begins to collapse in on itself. But if the star is more than about 20 times more massive than the Sun, the collapse is so violent that a supernova occurs, a huge explosion of the outer layers. The core of the star continues to collapse and nothing can stop it, which creates a singularity where the density is infinite. An event horizon forms around it, a boundary from which not even light can escape. The history of black holes is interesting because it is a mix of theories, philosophy, mathematics, and a bit of science fiction. In the 18th century, John Michell and Pierre Simon Laplace considered so-called dark stars objects whose gravity is so strong that not even light can escape. In 1915, Albert Einstein published the General Theory of Relativity, which describes how matter curves spacetime. And Karl Schwarzschild, who found the first solutions to Einstein's equations, found a spherically symmetric black hole. Around 1930, Subrahmanyan Chandrasekhar showed that stars with sufficient mass cannot be stopped by gravitational collapse, leading to the possibility of a black hole. In 1939, Robert Oppenheimer, together with Hartland Snyder, predicted the collapse of a massive star into black hole. But at the time, it was considered a mathematical curiosity, not a reality. In 1967, John Wheeler popularized the term black hole, and modern theories of black holes emerged, such as rotating black holes, charged black holes, etc. Penrose and Hawking formulated mathematical proofs that black holes and singularities are inevitable under certain conditions. The 1970s to 1990s were observational years. In 1971, Cygnus X1 was the first candidate for a black hole based on X-rays. Stephen Hawking came up with the theory that black holes evaporate radiation, calling Hawking radiation. In 2019, the Event Horizon Telescope (EHT) took the first image of the shadow of a black hole in the galaxy M87. This marked a historical milestone or the visualization of what had been only a theory for decades. And today, black holes are considered a common part of the universe. They are found in the center of galaxies, they are formed when stars collapse, and even primordial black holes from early universe are considered. A white hole is a hypothetical object that is created when physicists reverse time in the equations of a black hole. The mathematics describing an object that does not let anything in but can spew matter and energy out, so they gave it the name white hole, or time-reversed black hole. There is no evidence yet that white holes exist or have existed in the universe in the first place, but some theories suggest that a white hole could be the exit from a wormhole connected to a black hole. And in loop quantum gravity, it is speculated that the final collapse of a black hole could bounce back as a white hole, which could solve the problem of information in black holes. The differences between black holes and white holes are more hypothetical, as a white hole has not yet been confirmed, but through theories and calculations, we are able to dedicate what the differences are and what their properties are. A black hole absorbs everything, unlike a white hole, which throws everything away. Both allow a one-way path, a black hole only inwards and a white hole only outwards. A black hole has been confirmed and observed, while a white hole is only hypothetical from calculations of Einstein's equations when we create time reversion. A black hole is formed by the collapse of a massive star and can evaporate via Hawking radiation, while a white hole may form as a result of a black hole or a wormhole, and is possibly unstable as its event horizon could collapse rapidly, or it could interact with its surrounding matter, causing it to collapse. Finally, I would like to address my own theory regarding white and black holes. If we discovered a white hole and it functioned as a wormhole with a combination of black holes, we could advance technologically and the exploration of the universe would move to another level. With this knowledge, we could enable the teleportation of objects and living beings, but only under certain conditions. First, we would have to make sure that this wormhole does not break things down into atoms. If it does, then we would not be able to use this form of teleportation. We also need to find out how white holes are created, which could allow us for manual creation, which would allow for the teleportation of objects even from home, since we already know how to create a black hole using particle accelerators, although they would be so unstable that they would evaporate immediately, so we would have to find a way to extend the life of the given black holes and at the same time stabilize them enough that they would not be catastrophic for the entire planet. But in order to use this form of teleportation stably, we need to make sure that we can keep the white hole stable. If we meet all these conditions, we can think about what we can do with this technology and what it would mean for us. If a black hole acts as a door to a wormhole, then if we create or find one or two near us, we could travel throughout the galaxy, the universe, or even the multiverse, which would open a new door to my theory. What if we discovered a new form of life outside our planet? This could mean that aliens exist and we could test our theories and experiment on them, unless of course they are as advanced as humans. If they are as advanced as humans, we could potentially have cooperation between life forms, but we would have to communicate to do so. But if they are not so transverse, then the first non-world war could arise, which could cause the extinction of a planet and its population, which would cause consequences that could last until the end of the existence of one of the given species. But if they are more advanced than us, they could enslave us so that we would be on the same level as animals in a zoo or a slaughterhouse. If we manage to discover a new universe which would confirm our theory of the multiverse, and we could find out if the conditions in our universe are the same as in the newly discovered one. And finally, for this theory, if we discovered a new universe and started using white and black holes as portals through which we can travel, we could use it both positively and negatively, and it could have both very positive consequences and catastrophic consequences. Therefore, we should be careful about what we do and where we poke our noses and what we experiment with.